Welcome. Let's continue from past work with matrices. In this section, I will show the equivalence of Cramer's rule and Gauss elimination method. We have done Gauss elimination method in the previous in the previous videos, and I'll try and shed some light on determinants. In the previous videos, we've been talking about Gauss elimination and how to determine the Gauss elimination expressions. I used water as an example to show the physical concept of matrices and showed an example method of getting the values of the unit measures by the Gauss elimination method. In the current video, I will expand upon the Gauss elimination method and show how Cramer's rule could be determined or derived from the Gauss elimination, thus showing equivalence between the two. Let me show you a previous slide. This is the beginning of the simplification of the algebraic expressions we got from the reduction of matrix in a row-reduced echelon form. So from that row-reduced echelon form, we got this expression for x, and then we ended up substituting the values of a1, b1, c1 into these expressions for x, and the value of x thus derived was 100. Unknown unit measures x, y, and z, similarly y and z, can be calculated by substituting the values of the coefficients a, b, and c from this matrix and k1, k2, k3 from this matrix. However, there is a very high likelihood that these expressions would fail, because if any one of these values is 0, say for example b3 is 0, then it would be impossible to determine the value of this expression. Or if this value right here, the denominator is 0, then again there will be an issue. But we should look at the symmetry, and that is what I'm going to present in the next slide. Look at the symmetry of the operations in the current slide. The symmetry of the operations in the current slide shows the value of x derived from the expressions of the Gauss elimination before. And look at the numerator. The numerator has no values that are ai's. There is nothing like an a1, a2, a3 in the numerator for the value of x. Similarly, numerator for the value of y does not have the coefficients, initial coefficients b1, b2, b3 for y that were in the original matrix. And for the coefficient of z, there are no, and for the expression of z in the numerator, there are no coefficients c1, c2, c3, which are kind of replaced by k1, k2, k3 here. Similarly, in the expression for y, all the bi's are replaced here by ki's. And same for the expression for x. The ai's are missing, and instead you find ki's. Symmetry in the previous expressions should bring about a slight hint that we are moving towards a Cramer's rule. Let's try and simplify these expressions further. Simplify the numerator in divisor and dividend expressions. And what we end up is k1 divided by a1 minus k3 divided by a3 minus k1 divided by a1 minus k2 divided by a2. These can be substituted as k1 a3 minus k3 a1, k1 a2 minus k2 a1 divided by b1 a3 minus b3 a1, b1 a2 minus b2 a1. Here a1 and a3 cancel out in the numerator as well as in the denominator right here. The denominator, instead of k1, I have a c1 here. c1 a3 minus c3 a1, b1 a3 minus b3 a1, and so on and so forth. This comes out right here. Cross multiplication in the numerator and the denominator. Let's try to cross multiply k1 a3 minus k3 a1 times b1 a2 minus b2 a1, and k1 a2 minus k2 a1 multiplied by b1 a3 minus b3 a1. The expression in the numerator and the denominator comes out right here as Z is K1A3 minus K3A1 multiplied by B1A2 minus B2A1 minus K1A2 minus K2A1 multiplied by B1A3 minus B3A1. I must stress that I used these boxes instead of brackets or parentheses. So I hope you wouldn't mind. Gauss elimination, the solutions continued, or the simplifications are continued. Simplifying the expression given in the earlier pages by cross multiplication, we can get the following expression for Z. Note the two quantities in the numerator and the denominator, these ones, that get cancelled out in the simplification. I will use these two quantities in the coming videos, but for now, note that this cancellation allows us to convert the linear expressions of Gauss elimination into Cramer's rule. These cancellations right here will allow us to derive this expression right here. And note that this last expression is very, very akin to the Cramer's rule, because this expression in the denominator is frankly the determinant. We get Cramer's rule from Gauss elimination. Cramer's rule is the resultant expression like this. It is the variable determined as a ratio of two determinants. These two determinants. The top determinant in the numerator is the determinant of the matrix where the coefficients AI, BI or CI, which is the column for the variable that is in question, here it's CI, is replaced by the results column, that is K1, K2, K3. And the determinant in the denominator is the determinant of the matrix of the coefficients without any replacement. Repeating the simplification for x, y from slides 4, 5, 6 will lead to similar expressions for the Cramer's rule. But if you were to follow the similar instruction given on the previous slide, here for x we simply replace K1, K2, K3 instead of A1, A2, A3 in the numerator determinant and keep the determinant in the denominator as the original determinant. Similar expression for y is given here.